Hi, I'm Srivatsava, and in this video I'll be talking about my juice focus analyze exercise of secondary metabolite diffusion during solvent extraction. Before going to this part, I'll clear about some technical jargons. So what is a secondary metabolite? These are organic compounds produced by certain species in a phylogenetic group. Rather than that, these are organic compounds which are produced as a response to environmental stimuli. And these are multifunctional, and because of which their extraction has become very important industrially. As an example for the secondary metabolite, let us take the mycosporin production in marine organisms. These are called mycosporin-like amino acids and are abbreviated as MAA, mycosporin-like amino acids. Now let us investigate the chemical structure of one of these mycosporin-like amino acids. So if we look into this structure, we have a methoxy group, amino acid substituent, central cyclohexanone ring, and two alcohol substituents. As per the principles of organic chemistry, some of the important properties like solubility, temperature are dictated by the dominant group. Now we see that this cyclohexanone ring is the dominant, and we approximate the solubility to be equal to that of cyclohexanone. What we consider here is that the delta effects produced by methoxy group, the alcohol substituents, and these amino acids are negligible. Our aim here is to extract MAA. So industrially it is extracted using the method of solvent extraction. What is solvent extraction? It is the method of separation of organic compounds based on relative solubilities in different immiscible liquids.
The technique of liquid-liquid extraction is a form of solvent extraction which is often referred to simply as a separation, and we do this using a separating funnel as shown on the screen. The technique can be used in a range of contexts, and it's important that you understand why you're carrying out a separation in the experiment that you're doing. In this demonstration, we have a solution of a product of a reaction in an organic solvent, which in this case is diethyl ether. We are going to wash the solution with water to remove impurities which are water soluble. The first step is to remove the magnetic stirring flea from the reaction flask, and we need to wash this with ether to ensure that we don't lose any of our product. We now need to pour the solution of our product into the separating funnel, taking care to avoid any spillages, so it's wise to use a small glass funnel as we pour. Then we can rinse our reaction flask with more ether to ensure that no product is lost. Now we add the water which we're using to wash our reaction mixture with. It's important that you pay attention to your script, which may specify a different solvent and a particular volume that you need to work with. Next, you need to place a stopper in the neck of the separating funnel, and you must ensure that you don't allow this to fall out at any point while you're handling the apparatus. Secure the stopper with one hand and carefully invert the separating funnel. Now you can gently shake the funnel while periodically opening the tap to release pressure. Normally you carry out these steps several times to ensure thorough mixing of the two layers. And then with the tap closed, you can carefully replace the funnel in the ring on the clamp stand. Here you can clearly see the two separate layers in the funnel. In this case, the denser aqueous layer is at the bottom and the ether layer is on top. However, you should never make assumptions about which layer is which, and you may be given instructions that tell you how to test which layer is organic and which is aqueous. Before running any solvent out of the funnel, you must first remove the stopper. Not doing so is a common error which will prevent the solvent from running freely. Now you should place an appropriately sized conical flask under the separating funnel before carefully opening the tap to allow the lower layer to run out. You should watch patiently as the interface between the two layers moves towards the tap so you are able to stop the flow once all of the lower layer has been removed. Remember that in this case the lower layer was the aqueous layer. Now you can remove this flask and place a second clean conical flask under the separating funnel to collect the upper layer. As always, you should check your script to see what you've got to do next. You may be expected to return one of the layers to the separating funnel to carry out further extraction steps. In this case, however, we are simply going to dry the organic layer using magnesium sulfate. Other drying agents that may be used could include calcium chloride and sodium sulfate, so make sure you read the script before proceeding. If the drying agent forms clumps as shown here, that's a sign that the solution is still wet and that more drying agent is required. When you can see a snowstorm effect like this, you know that the solution is dry and that no more drying agent is needed. You can now remove the drying agent by gravity filtration before consulting the script once again to identify your next step.
Now, let us analyze the diffusion of secondary metabolites across the cellular membrane during solvent extraction. So, before deriving the mathematical part, we need to have some valid assumptions. We assume that microbial cell has spherical symmetry. Secondly, there is only radial flow of the secondary metabolite, which means that the concentration is a function of radius rather than theta and phi. We assume that solubility of mycosporine-like amino acids is equal to that of cyclohexanone. So, which implies that the partition coefficient of MAA is equal to cyclohexanone. Properties of cytoplasm present in the cell can be approximated to the properties of water. And during the extraction process, there is no reaction between solvents and the solutes. As our aim is to mathematically analyze this situation of solvent extraction, we will start with the general mass balance equation. Plugging in the relevant terms in spherical coordinates, we are left with equation 1. Simplified form of equation 1 is given in equation 2. Dividing throughout by molecular weight of the secondary metabolite, we will end up with equation A. Using Fick's law for the correlation and assuming no bulk motion, we end up with equation 3. Substitution of the above equation connecting time gradient of concentration and molar flux, we get equation B. So, equation A is used to get flux profile, whereas equation B is used to get concentration profile. To find the concentration profile, we consider equation B. Here, the assumptions are there is no further production of metabolite, which implies dou Ca by dou T equal to 0. And assuming no reaction of solute and solvent, we have Ra equal to 0. Finally, we are left with equation C. Solving equation A and C with the initial assumptions, we get the final results for flux profile and concentration profile as follows. So this is how we have analyzed the secondary metabolite diffusion across the cell membrane during solvent extraction. Thank you.